Okay, so welcome to Math 333 problem solving. And so what we're going to do today is we're finally going to finish the problem on the triangles and rectangles and then talk about another similar problem briefly. So we talked before about how without loss of generality, we want to say it's enough to just consider a isosceles right triangle. And we talked about what we needed to do in the case of an isosceles right triangle. We can spread out the base, we can contract it, and we saw that it just linearly scales the area of the two rectangles, the area of the triangle, so the ratio is unchanged. We can do that on the left, so we want to say we've now solved the problem. The challenge is, what if we don't have a problem that's in the same shape as the triangle we have here? And so, over here, this vertex is between the other two vertices. And that's leading to really nice intersections where it's hitting over there on the top, it's hitting over here as well. And that may not be the case in general. So the real warning in a problem like this is that the picture can sometimes be misleading, and we have to consider a generic triangle. As soon as we start drawing a triangle, we have to be a little bit concerned. So we had talked about what if we had some kind of strange obtuse angle on the bottom. And so what I did in the interest of time, and given that I have made some algebra mistakes in the past, is I just did the algebra at home. And so I said, let's consider an obtuse triangle. And let's see if we can just run the arguments we did before. And we have to be a little bit careful, but without loss of generality, you can always assume two of the vertices are 0, 0, and 1, 0. You can just orient the triangle like that. And then we'll have the other vertex at r, comma 1. Now you could say that this is not the most generic possibility. We maybe should have r, comma h for some height h. But if we had some other height h, we could just linearly rescale things. And that would change the area of the triangle and the area of the rectangles by the same factor. And so it doesn't really matter what the height is. To make the algebra easy, since I was doing this while my daughter was doing gymnastics, I just chose h to be 1. If you're concerned, go through and do it for general h. The other way to look at it is just think that we're measuring the x-axis in feet and the y-axis in yards, and just have some kind of rescaling like that. All right, so we want to look at what would be the area of two rectangles. What's the best we can do? And so I said, well, let's assume that one of them is at a, comma 0 for its left endpoint, and then the other one, let's assume, is at b, comma 0. And then we have to figure out what are the remaining three vertices of each of the two rectangles. I'm not going to go through the algebra. It's not too bad. We just have to write down the equation of the lines. And so for the first one, if we do this line over here, the line from 0, 0 to r1, then that's where we get the equation y minus 0 equals the slope 1 over r times x minus 0. Or we just get y equals x over r. So it's not too bad to get the equation of line for that. We're not using any advanced mathematics. Normally in Putnam problems, you don't have to use advanced mathematics. Now we look at the next line, the line from 1, 0 to r1, and the slope is slightly different and the point is slightly different. But again, it's not too bad to write down what is the equation of the line, and then we can just simplify it to x equals r minus 1, y plus 1. And the question is always, what's the best way to present the information? Do I want y as a function of x, or do I want x as a function of y? Let me write both of them down. I have no faith in my ability to do A3, A4, A5, A6. I'm not even going to look at them. I'm going to spend all my time on A1 and A2. It's worth spending a few extra seconds to write both expressions down so that whichever one I need, I'm going to have it readily available. So I have both of those now. And now I just start to find what are the coordinates of the other points. And so for the lower one, we already knew we had A0. Well, now we go up from A0 and see where do we hit the side. And that's going to be A and then A over R for over here. And then similarly, we can do the other ones. I just realized that by writing it like this, if I want to erase, I'm going to erase that one because I did that first. So I'll just write it like this, A over R. And so we can similarly go through and find what are the other vertices. The next one down here that one requires a little bit of work, but we see that that one is 1 comma a over r. The x-coordinate clearly is going to be 1, and just how high up are we going? Well, it's the same as what we were doing a moment ago, so not a big deal. Now we look at the next triangle, the next rectangle, and we know we start off at B, and then just how high up do we go? Well, it has to start at the same height as the other one, so it's got to start off at B a over r. So this point here, let's shift to another color. This point here would be B and then B over r. I'm sorry, not B, A. No, B, sorry, B over r. It's at the, no, A over r, sorry, A over r, because it's at the same height as what we had a moment ago. And that's where this one comes from. And the next one, B over r, is just going all the way up to here. And still has the same x-coordinate. So now this one over here is going to be B over r. This point down here and this point down here, we know what their x-coordinates are. We just have to find their y-coordinate. Well, since we know their x-coordinate, that's telling us we want to use, I think, this formula. Because for that formula, if we know the x-coordinate, we get the y-coordinate. So when we plug all that in, when the dust settles, we now have the vertices for all of the stuff. And so I'll just write the one down here. This was going to be 1 plus, oh, I'm sorry. It's the other way around. Sorry, my bad. It's the y-coordinate that we know, right? We know the height. We want to figure out the x-coordinate. This is the equation we want to use. We know the y-coordinate. For the bottom, the y-coordinate is a over r. For the top, it's b over r. So use with y equals a over r, then y equals b over r. And when we use that, then we can get the coordinates. Okay, so that wasn't too bad. And then once we put all that in, now we have the coordinates. And down here, we will get that this is going to be 1 plus r minus 1 over r times a. And then, or did I drop something? I dropped the y-coordinate. B over r. And then there should have been over here, or yeah, I'm missing the y. I'm missing the y-coordinate. And the y-coordinate there is just a over r. I just forgot to include it. I included it for the other one. So we can now calculate what the area of the two rectangles are. So for the first one, it has a length of 1 minus a, and it has a height of a over r. And so that's where this first one comes from, length times width. And then for the second one, it's a little bit more algebra to go through, but again, we know the height is going to be b over r minus a over r. And then we can just look at the x-coordinate difference. And so we have our formula for a. So again, this is going to take a little bit of time. You have plenty of time. You have 3 hours. I'm not doing any advanced math here. I'm just writing down equations of lines. There is almost surely a better way to do this problem. But this is a way that I know is going to work in a reasonable amount of time. And so once I have this, I now have my formula for a. So the area function is going to be 1 minus a times a over r, et cetera, et cetera, et cetera. And so now we play the exact same game as before. We fix an a and say for that fixed value of a, what's the best b we can choose? And we know b is going to be at least a, and it's going to be at most 1. And so we want to figure out what's the best value. So how do we find the best value? We take the partial derivative with respect to b, set it equal to 0, and check the endpoints. Well, if we take b equals a, we're getting no area, so clearly that's bad. And if we take b equals 1, we're not getting as much area as we could have. We're basically getting 0 area again. So we don't have to worry about the endpoints. So we take the partial derivative with respect to b, and we get the following expression. And now we just have to set this equal to 0 and find what is the relationship between b and a. And when the dust settles, we get b is 1/2 plus a over 2r. So this satisfies a lot of good things. First of all, it's going to be larger than a, right? And so now what we do is, now that we have that, we can plug that back into the formula for a, and so we'll come up with a new formula. Today. Okay, so yeah. So I just did this in Mathematica because I was lazy. So here is my new area function. I take the old area function and I place for b the value of a. And I asked it to simplify the area function. And so when it simplifies, it should be going to this one over here. So that's the simplified formula for the area. Right, it's a function of a. It's not a horrible function of a. And if you look at it, it's quadratic in a. So the derivative is not going to be that bad to calculate. The algebra is not going to be that bad. So we take the derivative, we set it equal to 0. Again, you will not have Mathematica on the Putnam, but have you seen Ender's Game or read the book? So, they have the commander has the hook that he can just use, and he can basically do things that the other students can. It's good to be the professor. So as the professor, I can just use Mathematica and say, hey, take the derivative, set it equal to 0, solve a. It's very, very straightforward. And you get a is r over 1 plus 2r. And then we plug that in to find what is the best value, what's the maximum area we can get. And so we had, this was the area function. And so now the best fit value comes down to here. And that's really interesting. 1 plus 1 over 2r. If you remember what we had before, and this is one of the reasons why I love lecturing like this, because I can now just easily toggle back and see what we had. The best area we had before was 1/3 when we looked at isosceles right triangles. That was the best we could do. So the best we could do was 1/3. What are we getting down here? 1 over 1 plus 2r. But if you look at it, what is capital R? Well, we have an obtuse triangle, so what must be true about R? So what can you tell me about the magnitude of R if this is going to be an obtuse triangle? Greater than 1. And if R equals 1, we would have a right triangle. If R equals 1, have a right triangle. Well, look at the formula we get. 1 over 1 plus 2r. So if r is greater than 1, 1 over 1 plus 2r is less than 1/3. If r equals 1, 1 over 1 plus 2r equals 1/3. That's really nice. That lets us know that it is quite likely we have done the algebra correctly. Because we know when r equals 1, it should reduce to the isosceles right triangle. It should reduce to the right triangle that we've considered before. And we are seeing that. And so in terms of what is the answer, because you always want to make sure on these problems, you might have done all the math right, but if you don't answer the damn question, you're going to lose points. What is the question? Find the maximum value or show that no maximum exists of the following. So the question is, Do they give you a triangle and do you have to do things with that orientation, or do you get your choice of how you do things? So if I give you a triangle like, well, if I give you a triangle like this, do I have to put the boxes in like this? Or do I have the option of putting in the boxes like this and just choosing whichever way does best? It says T ranges over all triangles. And so what I would say is, since T ranges over all triangles, without loss of generality, we can always assume it's oriented so that if there is an obtuse angle, it's up on top. We would be in trouble if maybe for the obtuse triangle, if you could get larger and larger strings, sequences giving larger and larger relative areas. But here I would say that the largest value is going to just be 1/3. So there's a lot of stuff that I really like about this problem. I think this is one of the best problems I've seen to highlight how should you attack something. It can be daunting at first. And when you see something like this, it's easy to just get overwhelmed. So stop, pause, have a piece of candy, drink some water, do something to just calm down, relax, and say, let me gather some data. Let me be an experimentalist. Let me try to look at some simple problems, some simple cases. This wants us to have T range over all triangles. Screw that. Let's let T be a nice triangle and try to build some intuition from that. And then once we have that, then we can say, okay, is it possible to reduce the general case to what I already know? So this is where mathematicians triumph. We try to reduce things to previously solved problems. Have I told you the joke about the mathematician, the engineer, and the burning house?
Yes.
Yes. So that's what you should be thinking of right now. Except, of course, don't ever do that in practice. But can you reduce the general case to what we've just done? And then the last 2 bits of warning is you could do this as a multivariable calculus problem. We have A and B, X and Y that we're going to simultaneously be and we want to optimize. But that might require you to remember your multivariable calculus. And it's often dangerous to ask people to remember their multivariable calculus. So if you forget multi, screw it. And remember that in many regards, multivariable calculus is just single variable calculus multiple times. It takes me less than a minute to teach people the general theory of how to compute a partial derivative. Pretend y is fixed, and then just regard it as a function of x. That's it. Now, when is a function of 2 variables differentiable? It's not the case that the 2 partial derivatives existing implies the function is differentiable. That's different. But to actually compute partial derivatives, it's trivial. And so over here, if we have 2 variables, let's just treat it as a 2-step process. First, fix A and vary B and see what B is best for given A. And now we have a problem of 1 variable. And so this is a general idea, in some sense, reducing dimensionality, trying to make the problem easier. And then the last warning for a problem like this is be very careful that a picture might mislead you and you might not be considering the most general case. That over here, we have, for the triangle T, the rectangles S and R, they're both hitting the side walls on their top. That's not the case if we have an obtuse triangle. So we just have to be careful about something like that if the obtuse angle is in the top vertex and not on the bottom. I'm sorry, if the obtuse angle is on the bottom and not on the top. So just be very careful that the picture could be misleading in terms of the configuration. And you might just have to break things into cases. Case 1, the top vertex has x coordinate between 0 and 1. Case 2, it doesn't. If you have freedom in terms of how you orient the triangle, you could always orient it maybe so that the obtuse angle, if it exists, is at the top vertex. But then, depending on how you're putting in the rectangles, you may not be able to do this. The last comment for this problem is this is how you now generate research. We could ask about a generalization. Instead of putting something in a triangle, what if I gave you a three-dimensional shape? What if I gave you a cone? What's the best you could do? Well, the difficulty is, for a cone, I can't really have the two angles different. For the triangle, I can have the two slopes of the sides different. But if I had a cone, that would not be the case. The angles, this angle here and this angle here. If I try to sweep this out and make this a cone, spinning about here, then this is going to spin out to here, and this is going to spin out to a greater distance. And so, if I wanted to try to consider this, I could say maybe consider all cones. And maybe do the problem for cones. But you should always be thinking, how could I generalize? How can I push this to a higher dimension? Okay. So let's just talk a little bit about another problem, continuing our geometry theme. So we want to inscribe a rectangle of base B and height h and an isosceles triangle of base B in a circle of radius 1 as shown. For what value of h do the rectangle and the triangle have the same area? So my first thought is it's strange that they're asking for what value of h. What might you expect them to ask? Yeah, so they're saying we're inscribing a rectangle of base B and height h and an isosceles triangle of base B in a circle of radius 1 as shown. For what value of h do the rectangle and triangle have the same area?
And why is h?
I might have expected them to ask for more than just h.
I see. Maybe like also the height of the height of the triangle.
Right, but what is related to the height of the triangle? What other number or parameter might you think would play a role in addition to h? Okay, well, without loss of generality, what is the radius? Right, without loss of generality, the radius equals 1. So what other thing in addition to h, what else might play a role?
Oh, I see. Like probably the angle, so like the border of the circle.
Well, but there's a more obvious symbol that's on the page. It's asking for what value of h?
Oh,
maybe B, right? So the question is, why no B? Why is B ignored? So the question is, if you know H, do you know B? Well, let's think.
I think yes, because depending on the age, there's only one rectangle you can make from that.
Exactly. So we could look at something like this. This would be 1. This would be H halves, and this would be B halves. So H halves squared plus B halves squared equals 1, or H squared is 4 minus B squared. Or B squared is 4 minus H squared.
Where's the H origin?
I'm sorry?
Which triangle does that represent?
Well, say the triangle down here.
Okay, I see.
And then this would be B halves over here. And then this would be H halves. So once I give you B, I know H. Once I give you H, I know B. That's why they can say for what value of H. If I were writing this problem, I'm not a nice person. I would probably say for what value of H and B, maybe, to try to be a little bit misleading. Do they have the same? Because really, once you choose B, H is forced on you. Once you choose H, B is forced on you. So is it easy or hard to find the area of the rectangle?
Um, well, I guess, but it's only one equal,
Yeah. So what would be the area of the rectangle?
or I guess the
It's just BH. And if we want to do everything in terms of H, it would just be H times the square root of 4 minus H squared. And we want to set the area of the rectangle equal to the area of the triangle. I'm not going to do anything right now, but rather than setting the areas equal to each other, what might you set equal? When you see the square root, instead of looking at the area, what might you look at?
So is this for like comparing the area of the rectangle to the area of the triangle?
Right. Just something that I want to have in the back of my head. I see the square root and I'm not thrilled about having to do comparisons with the square root. So instead of trying to say the area of the rectangle equals the area of the triangle, what might I say instead that's equivalent? So instead of showing that the areas are the same, what would be an equivalent comparison that would get rid of the square root?
So these,
So instead of saying, look, instead of saying, I want the two areas to be the same, I want something that's going to be equal only if the areas are equal, but it's not going to have a square root. What's related to the area of the rectangle that has no square root? Instead of looking at the area, which has a square root, how could I get rid of the square root? I could study the
uh, I guess area of like this semi.
it's got to be the same object. It's got to be the same relationship. But in the Pythagorean theorem, you would have the square root. We often don't look at the distance. We look at the distance distance squared. So maybe, I don't know, but in my mind, I'm thinking maybe area squared is better. I don't know if that's going to be the case, but the point of this class is to just talk about thought process. As soon as I see that square, I don't think this is a problem I'm going to have to use differential calculus, but if so, I would definitely not want to look at something like this with a square root. I'd want to square things. And so if I can show that the area squareds are the same, then the areas are the same. How do I calculate the area of the triangle?
So this was so I guess we know the whole length is two.
Okay, so for the triangle, do we know the base? So what's the base? B. And what's the height? Do we know what the green line is? Do we,
Oh, I guess we know, okay, oh, I see. So I guess we know the radius is 1.
the radius is 1,
Which is the green line.
right?
You know, h over 2. So 1 minus h over 2.
Good. So the height
Right?
is 1 minus h over 2. So it's going to be 1 minus h over 2. And then because it's a triangle, I have to put in a factor of 1/2. So I can write this as 1/2 b, and I can replace h with b, but that's going to involve a square root. So do I want to write things in terms of h or in terms of
Probably,
h is good. So now if I go to area of the triangle squared, that's going to be 1/4 b squared 1 minus h over 2 squared. But what's b squared?
b squared is, I guess,
Well, what is b squared? We've solved for b squared already.
oh, I see, 4 minus h.
It's 4 minus h squared. And then 1 minus h over 2 squared, I can pull out a 1/2, and that's going to become a 2 minus h squared. Over 4. And the area of the rectangle squared is going to be h squared 4 minus h squared. So hopefully I can copy this. And so I think looking at squares is much better. And so when we do this, we get, h squared 4 minus h squared is supposed to be 1/16 4 minus h squared 2 minus h squared. And here is a general principle. Never do algebra until you need to. There is no need to expand and multiply everything out. What can I do to both sides?
1 minus h squared, and then square root both sides.
Okay, we could even square root both sides. So do I have to worry about dividing by 4 minus h squared? Is it possible that h could be equal to 2?
No, because if h is equal to 2, we don't have the rectangle.
Right, so if h equals 2,
You know, h is less than or equal to 2, because the diameter is
right, if h equals 2, then we're basically in the situation where we're going straight up and there's no triangle and there's no rectangle.
Yeah.
And then it's clearly not going to be hitting anything. So I'm not worried about that. So now, as you said, take the square root and we get, so take square root and we get h equals 1/4 2 minus h. Can we ignore the plus or minus?
Yes.
Yes. As we know, 0 is less than h is less than 2. Okay, so we get 4h equals 2 minus h, or 5h equals 2, therefore h equals 2/5. And that's clearly less than 1, so that's reasonable. And then what should you do at this point?
Well, does the original problem says
The original problem just says for what value of h, and we say h equals 2/5.
Yeah, so I guess.
Yes, exactly. So now that you've done this, check. Oops. Is the area of the triangle equal to the area of the rectangle? But in principle, we've seen how to do this, so I'm not too worried. So how might you generalize this? Well, instead of doing it on a circle, yeah, you could do it on a sphere. I have a box that I'm putting in, and I have maybe a pyramid coming out. And you could try to generalize something like this. So this problem did not seem to be that bad. So sometimes the problems won't be that bad, but you might give them too much credit. You might fear them too much. And for this one, as long as we don't lose our heads and just go and try to see, is there any information we can extract? They only ask for h. They don't ask for h and b. You said, inscribe a rectangle of base b and height h. Well, you can't choose any b and h. Once you choose one, the other is determined. So there's really that hidden relationship that they're not emphasizing. And now that we have that, without loss of generality, we might as well assume the radius is 1, and then we figured out what the areas were. If we hadn't squared things, and we kept things as functions of 2 variables, this would be a pain. So the key is you need to realize that there's a relationship between b and h. And so always think, does a choice of one quantity constrain another? That's really good advice. All right, so this is a good place to stop.